Okay, so in our last video we introduced power functions and we left off talking about polynomial functions. One thing we are going to make explicit here is we said any a sub I, right, for I, so any of these can be a real number. We do have to make the distinction that our a sub n, the first term, the largest one, is not zero, right? So we will make that distinction or else, right, the next one will be our a sub n, right? So just keep that in mind that the leading term, and here let's go over some of the terminology here. So each one of these we call a term of our polynomial, right? So in this case we look at a sub n is what we refer to as our leading coefficient. And this here is our leading term. Right, and then the n is going to be what we call our degree. Right, so if the largest power, and again, notice the way we write this is we write it in order from largest power to the smallest, right? If it isn't in this form, and if it's a polynomial, we can rewrite it, express it in that form by either multiplying or rearranging some terms if needed. Okay, so regardless if all these other powers, if this is 4 and then we got 3, 2, 1, etc., right? The degree is just the it comes from the leading term. Okay, so as some examples here. We want to, so for something like this, so we want to do two things. Determine the degree and end behavior of the following polynomials. Okay, so our first one okay, so let's say this was our polynomial. It's of degree 4. All right, so again, right, it's in order in terms of the highest power decreasing in each term next to it decreasing in power. All right, there's no cubic term, but again, that's all right. All that's telling me is that the coefficient of the cubic term is 0, so it's not represented in this polynomial. All right, so now when we're dealing with degree, right, and end behavior, really what we're going to focus on is the leading term. This is going to tell us all of the information for both of these quantities here, right? So from this, n is 4, so we have a polynomial of degree 4. All right. So the next thing is determine the end behavior, right? And what we mean by end behavior is this. What happens as x goes to infinity and x goes to negative infinity, all right? Now, we can do this without any kind of graphing utility, all right? We could take out a graphing calculator, use Desmos to just kind of plug this in and then determine it from there, but I don't even need to go through all that problem, right? All that hassle, right? When we deal with end behavior, as x gets larger and larger, right, what's going to take over is this leading term, right? All these values essentially become less and less significant as x gets larger and larger because this value just dominates the rest of these, right? It just gets bigger at a much faster pace, excuse me, because of that fourth power. Okay, so in the last video we looked at, okay, well, I know what essentially it's a power function. I know what this looks like, right? Even power and a negative coefficient. Well, I know that this has this behavior here, right? And notice just the leading coefficient, right? This can make the function have some interesting, we'll say, what's called local behavior, but I'm not worried about that. All I'm worried about are these large values. And this term is what's going to guide those values here. All right? And knowing that it's even, knowing that the leading coefficient is negative, I know it has something like this, some kind of shape like this. So what we can see here for the end behavior, as x goes to infinity, well then f of x also goes to negative infinity. Or excuse me, f of x goes to negative infinity. Now as x goes to negative infinity, the function values get more and more negative as well. So f of x also goes to negative infinity. All right. Okay, and that's how we identify the end behavior, right? The leading term is what's going to give us the end behavior. All right, so let's try one more example here. So let's take a look at something that looks like this. Okay, so now in this case, this doesn't look like our general form for our polynomial. But again, I can make it look that way, right? We just need to do a little work to begin with.